Greetings, hello, good morning, how are you? Thank you very much for watching my video. Today's video is what I call an information sandwich, and the topic I'll be discussing today is the file select register in the PIC microcontroller. In particular, I'll be looking at the file select register as it pertains to the 18 enhanced MCU family of the PIC-18. I call this type of video an information sandwich because I'm basically taking everything that I can find related to the file select register in the PIC-18F manual, and I'm cramming it into a video. So it may not do things in order and in the best way that's suited to learning. And on that note, I will mention to you, the listener, that I am learning. I am not an expert. I am learning, and even more, I'm actually going through a popular textbook on the 18F, which is dealing with the subject of immediate and direct addressing modes. And so when you start studying that topic, the file select register is going to come up a lot. So, I'm 2 minutes in here, and that's my introduction. Thank you for watching. So to begin with, I thought I would take a definition off of Google for the file select register in the PIC microcontroller. Surprisingly, file select register did not show up in the 18F manual glossary. So just Google search an answer. So now I will read FSR, file select register. It is the pointer used for indirect addressing. In the indirect addressing mode, the 8-bit register file address is first written into FSR. It is a special purpose register that serves as an address pointer to any address throughout the entire register file. Did you understand all of that? I understood a lot of it. Anyway, one comment before I really start getting into it. The FSR is not to be confused with the similarly sounding acronym SFR, which in PIC language and jargon is referring to a special function register. Well, I'm not going to go into an explanation of what that is, but an SFR is the opposite of a GPR, which is a general purpose register. And the name of a special function register is self-explanatory, so I won't go off about that. But I'm not talking about SFRs, I'm talking about FSRs. And I guess you could get it confused with the BSR. The BSR, which is the bank select register, and I'm not talking about that either, but what that is, well, I'll read. The structure of memory is effectively made up of 16 banks, each of 256 bytes. A special register, the bank select register, holds the bits that, well, anyway. So here we go. on the internet browser search, I typed in FSR, and it came up with 362 instances of the word FSR. Now, a good bulk of these search results deal with the instruction set and example code related to all of the different instructions, like X or LW, and so the FSR shows up in a lot of these instances. So a good number of these FSR search results deal with examples of the instruction set, and within the code there's a lot of FSR references. So on page 94 of the PDF, which hopefully I will have left a link down below for, shows where the FSR shows up in the General Enhanced MCU block diagram. So this is probably a great place to start. I'll just point out a few things. Okay, so here is the program counter, and not surprisingly that's over close to the program memory, the ROM. But really, when we're talking about the FSR, the file select register, we're talking about addressing of RAM. So not surprisingly, it's on this block diagram closer to the data latches of the data RAM of the device, over here near all the ports, and the addressing is showing the number 12, and that's because that is specific to why the FSR is being used here, because it's related to instructions beyond 8 bits. So there's a higher and lower byte. In the higher byte, I don't think all the bits are implemented, but I'm getting ahead of myself. So in PIC 18, there are different ways of accessing data, and this is commonly referred to as addressing modes. And so data can be in a register, or it can be in memory, or it can be provided as an immediate value. And I haven't explained it, but there are 4 addressing modes, and they are 1. Immediate, 2. Direct, 3. Register indirect, and 4. Indexed ROM. So I'll try to explain this briefly and quickly because I think it's important. So in immediate addressing, you're dealing with a literal. So you're dealing with some code that you wrote, and the literal value is literally contained within your code. That's immediate addressing. But direct addressing is when you're going into a RAM location and you're retrieving that information, fetching it. So in direct addressing, the operand data is in a RAM memory location, and the address is known. And in immediate addressing, the operand comes And so in immediate addressing, the operand comes immediately after the opcode. It may have been helpful if I put some sample code on the screen, but when you see some sample code with a literal next to it, that literal next to the opcode is immediate addressing, whereas in direct addressing you've got to go into a RAM file location. So, moving forward, this is a snooze alert because this will be very boring. I will be reading directly out of this manual. So FSR, instance 1, where FSR first shows up, we have this page here, which is dealing with, I guess, reset situations. And so it's talking about the initialization conditions for SFRs, I guess like the default state of the registers maybe. But anyway, FSR shows up here. So here's the first instance, which is FSR 0H and FSR 0L. So I believe these relate to the lower and high byte. So, yeah, there is the file select register, but there are also some special function registers which have the name FSR contained within the SFR. I'll talk about this one first, FSR 0L. This is for indirect data memory address pointer 0 low. And this one, FSR 0H, is for indirect data memory address pointer 0 high. In the register indirect addressing mode, a register is used as a pointer to the data RAM location. And in the PIC-18, 3 registers are used for this purpose. And only 2 are listed here. But anyway, FSR once again stands for File Select Register and must not be confused with SFR once again. The FSR is a 12-bit register allowing access to, say, the entire 4,000 bytes of data RAM space in the PIC-18. Anyway, so these, once again, FSR 0H and L are showing up in the initialization conditions for SFR registers, and it's coming just after the reset situations. And it seems like this chart shows the different states of all these registers during power on reset, brownout reset, mclear, watchdog timer, wake up via watchdog timer or interrupt. So I guess the state changes depending on the reset state, which is getting away from the discussion of this video, but I don't know. Does it look like the states change too much between all those reset states? You be the judge. Okay, so I brought it back to the general enhanced MCU block diagram, and hopefully it can be seen that in this addressing there is more than one FSR register. There's 0, 1, and 2. So what's that all about? Okay, so I started by talking about these reset conditions, and then it's talking about the state of FSR 0H and L. The bits are set up like that. I'll read the legend. So the U, so where's the FSR here? The U stands for unchanged. X's stand for unknown, unchanged. A dash stands for unimplemented. So if I scroll down, well, I scrolled up actually. So here's where I was. I scrolled down to the next instances of FSR, and I said there was 3 FSR registers, and they're broken into 2 bytes. The first 4 being unimplemented. Well, this is the next FSR register, which again is broken into 2 registers, a high and a low, but this is FSR1. How does that compare to FSR0 as far as all these bits and their initialization conditions on reset? I don't know. I have to stop and study that. But moving forward, there's also FSR2. I stopped and paused while I was recording, and the conditions of the bits on FSR 1H and 1L look identical to those of 2H and 2L. And if you don't believe me, politely, you can stop and pause it and check for yourself. Okay, moving on to the next instances of FSR. So it's showing up here on page 93, section 4, which is the architecture section of this MCU manual. And here's where that section begins. So first page, second page, where it starts discussing Harvard and von Neumann, and then we move a little forward and we've got mention of the FSR here. So I'm not going to cover this material because it'd probably be helpful, but it's getting off track. Okay, I'll just read this. Double word instructions. Some operations require more information than can be stored in the 16 bits of a program memory location. These operations require a double word instruction and are therefore 32 bits wide. Instructions that require this second instruction word are move FF is an example, but that's not what we're talking about, but apparently 12 bits for each RAM address. Anyway, literal value to FSR move instruction. 12 bits for data and 2 bits for FSR to load. LFSR, FSR number, and address. I'll continue reading. I don't know if this applies to all of the above or just this call instruction. Anyway, the first word indicates to the CPU that the next program memory location is the additional information for this instruction and not an instruction. If the CPU tries to execute the second word of an instruction due to a software modified PIC program counter pointing to that location as an instruction, the fetched data is executed as a NOP. Double word instruction execution double word instruction execution is not split between the two TCY cycles by an interrupt request. That is, when an interrupt request occurs during the execution of a double word instruction, the execution of the instruction is completed before the processor vectors to the interrupt address. The interrupt latency is preserved. Are you lost? I am a little bit. Don't know what all this means. Okay, moving on to the next instance of FSR. Then it brings us to the enhanced block diagram again. Well, looking at it again maybe isn't such a bad thing. Okay, wanted to introduce this. So, Section 5 of this manual is the CPU and ALU. And it's stuff I've really covered before in different videos. Maybe not in whole, maybe only in part, but anyway, some good stuff here to read. And not too long after, the instruction set comes up on PDF page 109. It's pretty important. I always have to refer back to this page. And yeah, so where is it? It shows up on page 111 as a mnemonic operand in one of the instructions, and it's LFSR. And the description is move a literal 12-bit to FSRX, second word. And it shows the 12-bit instruction. So I forget how this works. This is the... Okay. I'm going to change topics just for a moment. Okay, so let's talk about add LW. And just from memory, I remember that add LW is a 2-byte, 16-bit instruction, and of the 16 bits, the first 8 bits are set aside for the opcode, and the other 8 bits, the K here, the other 8 bits are used for the literal value of 00 to FFH. Okay, so I'm all over the place with explanation, but I have a reliable source that tells me a little more about LFSR, and it falls under register indirect addressing mode, and this is where a register is used as a pointer to the data RAM location. And that's where we got those 3 FSR registers, FSR 0, 1, and 2. Those 3 registers are for this very purpose. And once again, that purpose is as a register used as a pointer to the data RAM location. Once again, the FSR itself is a 12-bit register, allowing access to the entire bytes of data RAM space in your particular chip. And we use LFSR to load the FSR, to load the RAM address. Well, in different words, when FSRX are used as pointers, they must be loaded first with the RAM addresses, and that can be seen in a text example on P177. I'm trying to sneak in some text material, as if I'm talking like I know what I'm talking about. Anyway, next. Okay, so like this LFSR, which is a mnemonic operand, I have some sample code. You can't see, it's off screen. And the comment next to this LFSR is load pointer. And then you have to specify the RAM address. Well, you have to, like, the way this works is you take this mnemonic operand, which loads a pointer, and what this FSRX means is you have to specify whether it's FSR0, FSR1, or FSR2. So if you're going to use this in some code, you will first write LFSR, and then you will have to specify which one of these FSR registers it is, and then you will specify the RAM address. Unfortunately, I don't have the example code on the screen, but this LFSR takes two. When you're using it in your code, it takes two pieces of information. First of all, it takes which FSR register you mean, 0, 1, or 2, and then it requires a comma and then the RAM address. And this is to load the pointer. I won't even try and explain this, but section 7 is talking about the memory organization, and I don't even understand any of this, but it has to do with a table lookup, and it says copy byte to RAM at FSR0, increment FSR0. So I went back to the general enhanced MCU block diagram, and I'm noticing that underneath these FSR registers, whatever they're called, there's an inc and decrement logic coming from the ROM latch, and here's the ROM over here in the program memory. Here's the program counter. I don't know how that affects the table latch. Interesting, this table latch comes up here. ROM latch decodes whether we're incrementing or decrementing this file select register 0, 1, or 2. So I can't say I understand this code that appears on page 140 of the PDF, but it is talking about the table latch, which was in the enhanced block diagram, and it's talking about incrementing something, and perhaps FSR0. And there was that little increment decrement thing on the bottom of the FSRs. So you can really tell I don't really know much about this yet. One page further, incf FSR shows up here under a table lookup. Okay, now this is a couple pages further, talking about the memory. I'm not going to read this. I think I've read it before in different videos. I'll just read this paragraph. The entire data memory can be accessed either directly or indirectly. Direct addressing may require the use of the branch select register? Bank select register, excuse me. How embarrassing. I'll start that again. The entire data memory can be accessed either directly or indirectly. Direct addressing may require the use of the bank select register. Indirect addressing requires the use of the file select registers, FSRs. Each FSR holds a 12-bit value that can access any location in the data memory map. Well, here's kind of a definition of the bank select register. When A equals 1, the BSR is used to specify the RAM location that the instruction uses. It's a shame. I should almost read the whole memory section again to understand it. Anyway, I'll just read the parts dealing with the file select register, and specifically general purpose registers, so non-SFRs. Enhanced MCU devices may have banked memory in the GPR area. GPRs are not initialized by a power on reset and are unchanged on all other resets. The register file can be accessed, the register file can be accessed either directly or indirectly using the file select register, FSR. Some devices have areas that are shared across the data memory banks, so a read-write to that area will appear as the same location value regardless of the current bank. We refer to this area as the common RAM. Okay, next instance, special function register map. This is still in the memory section of the PIC manual, and here's FSR 2H, FSR 2L. Well, we said there were 3 of these registers, and they each have a high and low byte. So there's the 0 one, and here's FSR 1H. Indirect addressing, INDF, and FSR registers. Indirect addressing is a mode of addressing data memory where the data memory address in the instruction is not fixed. An SFR register is used as a pointer to the data memory location that is to be read or written. Since this pointer is in RAM, the contents can be modified by the program. This can be useful for data tables in the data memory and for software stacks. Figure 7.9 shows the operation of indirect addressing. This shows the moving of the value to the data memory address specified by the value of the FSR register. Indirect addressing is possible by using the INDF register. Any instruction using the INDF register actually accesses the register pointed to by the file select register, FSR. Reading the INDF register itself indirectly, FSR equals 0 will read 00H. Writing to the INDF register indirectly results in a no operation, although status bits may be affected. The FSR register contains a 12-bit address, which is shown in figure 7.9. This is figure 7.9. And where to start? Figure 7.9, FSR operation, indirect addressing. So here's the instruction executed, here's the opcode and the address. And the address, just to show everyone, is pointing to an address in RAM. And this is probably a mnemonic operand here. And the opcode is the instruction is fetched. And here's the file, bank select register. And it all goes into the file address equals INDF. And here's the file select register, 12. And it points into the file address of the address. And yeah, there are 3 indirect addressing registers to address the entire data memory space, 4096 bytes. These registers are 12 bytes wide. To store the 12 bits of addressing information, 2 8-bit registers are required. These indirect addressing registers are FSR0, composed of FSR0H and L, 2, FSR1, composed of 1H and 1L, FSR2, composed of FSR2H and L. In addition, there are registers INDF0, INDF1, and INDF2, which are not physically implemented. Reading or writing to these registers activates indirect addressing, with the value in the corresponding FSR register being the address of the data. If an instruction writes a value to INDF0, the value will be written to the address pointed to by FSR0H, FSR0L. A read from INDF1 actually reads the data from the address pointed to by FSR1H, FSRL, FSR1L. INDFN can be used in code anywhere an operand can be used. Okay, so this can be used kind of as an operand. I think I saw that in the code we looked at already. I'm not sure. If the INDF0, 1, or 2 register is read indirectly via an FSR, all zeros are read, 0 bit is set. Similarly, if INDF0, 1, or 2 is written to indirectly, the operation will be equivalent to a NOP, and the status bits are not affected. So just to be clear, we're talking about indirect addressing, INDF and FSR registers, and it continues on, and I'm afraid I'm going to have to read all this. Each FSR register has an INDF register plus 4 addresses associated with it. The name INDF subscript N and FSRN H, FSRN L registers are used, but depending on the INDFN address selected, the FSRN capital H, FSRN low byte registers may be modified. When a data access is done to the one of the 5 INDF locations, the address selected will configure the FSRN register to do nothing to FSRN after an indirect access, no change, INDFN, auto decrement FSR after an indirect access, post decrement, post decn, auto increment FSRN after an indirect access, post increment, post inc n, auto decrement FSRN before an indirect access, pre-increment, pre-inc n. Use the value in the WREG register as an offset to FSRN. Do not modify the value of the WREG or the FSRN register after an indirect access, no change. Plus WN. When using the auto increment or auto decrement features, the effect on the FSR is not reflected in the status register. For example, if the indirect address causes the FSR to equal 0, the Z bit will not be set. Incrementing or decrementing an FSR affects all 12 bits. That is, when FSRN L overflows from an increment, FSRN H will be incremented automatically. Adding these features allows the FSRN to be used as a stack pointer in addition to its uses for table operations in data memory. Each FSR has an address associated with it that performs an indexed indirect access. When a data access to the INDFN location plus WN occurs, the FSRN is configured to add the signed value in the WREG register and the value in FSR to form the address before an indirect access. The FSR value is not Note: accessing the +WN address causes indirect access. The address register is the addition of the value in the FSRN register and the signed value in the WREG register. If an FSR register contains a value that points to one of the INDFN, an indirect read will read 00H, 0 bit is set, while an indirect write will be equivalent to a NOP, status bits are not affected. If an indirect addressing operation is done where the target address is an FSRNH or FSRNL register, the write operation will dominate over the pre- or post-increment-decrement functions. Figure 710 shows the interaction of the FSR register and the data memory. Figure 710, FSR operation, indirect addressing. Here's the FSRN, and it's pointing down at the different banks, I guess. Don't quite even understand what this is. Whole thing's even saying, but that's the point of this video. Hopefully one day I'll understand it. Nobody here to ask. Okay, shouldn't have said that in my video. Oh well, it's there now. Example 7.6 shows a simple use of indirect addressing to clear RAM locations 20H to 2FH in a minimum number of instructions. A similar concept could be used to move a defined number of bytes block of data to the USART transmit register TX-reg. The starting address of the block of data to be transmitted could easily be modified by the program. So here's indirect addressing, clear F, FSR1H, clear high byte of FSR, move LW, 0x20, load low byte of 20H, move WF, FSR1L, label is next, clear F, post inc 1, clear register and the increment, BTFSS, what is that, bit toggle skip if set or something, FSR, I better get that right. I mean, I made a video on this before, so you think I would know what this means. It means bit test F skip if set. Bit test F skip if set FSR1L 4. Could that be the fourth bit of this FSR register, whatever it is? Go to next. Continue. Okay, so now I'm looking for the next instance of FSR. I don't think I'm going to read all this code, but it shows these file select registers coming up in some of this code. So let's just read what this is even talking about. Initialization, example 7.7, that's this one here, shows how the bank switching occurs for direct addressing, while example 7.8 shows some code to do initialization, clearing of general purpose RAM. Okay, and we're dealing with the FSR in those instances. Just briefly, I need to initialize RAM to zeros. What is the easy way to do that? And I read it, I don't get it, so pause and read, but the FSR1H comes up. I'll just read the headings. Example 8.1, which is this, shows the initialization of the table pointer and FSR0 register to read the value from program memory to RAM buffer, starting at address RAM buffer. Example 8.2 shows the sequence to initialize these same registers and then write a word to the internal EEPROM program memory. So now moving down to page 194, it's talking about high priority interrupts, interrupting a low priority interrupt service routine. Figure 10.5 shows a high priority FSR with a low priority interrupt pending. So here's figure 10.5, high priority interrupt with pending low priority interrupt. And kind of neat, now we're on page 194 of the reference manual, and I click down for the next instance for FSR, and it takes me to page 658. So that's kind of interesting. We went from page 194 to page 658 with no instances of file select register, not as an acronym anyway. So what's this talking about? This is an introduction, and this is under the section of the instruction set. So I'm not going to read all of this introduction. It does say that in the 18F some new instructions have been added that require 2 program memory locations. I think we're talking about FSR anyway. Okay, this is a little important to read. The instruction set, talking about all the instructions in the 18F family, the instruction set is highly orthogonal and is grouped into 4 basic categories: byte-oriented operations, bit-oriented operations, literal operations, and control operations. And under the literal instructions may be used some of the following operands: a literal value to be loaded into a file register specified by the value of k, the desired FSR register to load the literal value into specified by the value of f. So, back to a very popular reference point in this manual, which is like page 109 thereabouts, which is talking about CPU and ALU, but then it starts talking about the mnemonic operands in the instruction set, and it breaks all of these instructions down into different categories: byte-oriented file register operations, bit-oriented, and control, and literal operations. So what does that mean? I mean, what's the defining characteristic of a literal operation? Well, for one thing I can tell, and I'm thinking this through out loud as I talk, which is always dangerous, but a literal L appears in the mnemonic operand. Add LW and LW. So here's this literal operation LFSR. Move a literal 12-bit to one of these FSRs 0, 1, or 2, and then I think, what did this require? A RAM location? Can't remember now. So, okay, all these operations deal with literal values. So I guess, what did that fall into the category of? I mean, reading from a text source under the topic of immediate addressing mode, it has to say that in this addressing mode, the operand is a literal constant. So, when something is immediately addressed, it means that the, what do you call that, literal, the constant, is directly referred to. The text says it better than I can. So yeah, I guess add LW and whatever your literal constant is. So that's why these are literal operations. Yeah, here's a chart of what these are. Opcode, and then the literal value. Once again, I'm at this final well, close, no, not final, but section 31 of this reference manual, which is the instruction set. The section of the manual contains the following major topics. Pause and read. And then it, well, broke them down into different categories, and then it says in these literal instructions may use some of the following operands. The desired FSR register to load the literal value into. I can kind of see what it's saying there. I have a hard time putting that into words. Like there's that, I guess it was LFSR was the op code. And so then you would write that and then just, I better not talk out loud. Think out loud, I shouldn't do that. Okay, so I'm going to scroll down to the next instances of FSR. There's the LFSR. It's got an F and a K, so you could, so you have to specify, oh, I talked about that before, right, in my text? So I looked it up in some sample code in my text, page 178 if I want to look. LFSR, and then it specifies a 0, and then the RAM address. So this would be LFSR, or like FSR 0, 1, or 2. So that's what this F represents. And this K, which is a literal, but this K would actually represent a RAM address. I'll just read this out loud even if I don't quite understand it. Move literal 12-bit first word to FSR specified second word. And it looks like it's one of these 32-bit instructions, which is really a rare thing. There aren't many of those. Call, go to, move FF. Okay, now I'm down here. FSR, any one of the file select register pairs, such as FSR 0H, or L, or 1H, or 1L, or 2H, or 2L. This is still under section 31. Still section 31. Indirect addressing symbols. I don't know what the asterisk means, but there's an FSR N selects INDF-N register. FSRN++ selects post-inc N register, post-dec N register, pre-inc register selects +WN register. Boy, do I need a lesson. And here's another instance of it. Add WF, and this example is using this FSR 0 low byte. I don't even know what it's talking about. But it takes, even if I don't quite understand it, it's processing two pieces of information. Well, no, I was thinking of that LFSR instruction. Never mind, forget what I just said. But what's it taking here? Two pieces of info, 1 and 1. What does that mean? Okay, add working register to a file. So hopefully the working register is loaded and it would be added to this file. But then what do these pieces of information specify? Like maybe the destination bits? Must be. And I can't remember. If WREG was that destination bit 1 or 0? Okay, P28 as a reference. If you want to have like a Okay, if you have like a destination bit, which I think that's just happens to be 2 of them here, I have in my text, tells me that the destination bit for WREG is 0, which makes sense because I think we're adding information to both the FSR 0, high, and low. So we don't want the destination to be WREG, so we don't want zeros here. And because there's 2 of them, it signifies that because there's 2 different registers, a high and a low byte. So I think that's what these are. There's 2 1s because they're both destination bits, and the 1 signifies a file. And there's lots to do with the FSR in this section 31, showing sample code for all the different types of instructions. Is that what's going on here? And all these extra instances. Section 31 dealing with all these different instructions have FSR registers in the sample example code. But perhaps this is important. I just stumbled across it, really. Page 738 of the reference manual starts talking about LFSR, load 12-bit literal to FSR. Syntax, LFSR, file, and then the literal. I'll just read. The operands are between 0, like equal to it, or 0 is less than the file. What does that F stand for? And equal to, or 2 is greater than that. And then the operands are between 0 and 495, so those are like memory locations. Operation K FSRX, so I guess you can specify 0. I don't want to comment out loud. Description. The 12-bit literal K is loaded into the file select register, FSR register, pointed to by F. So this F is for F equals 00, FSR 0, F equals 01, FSR 1, F equals 10, FSR 2, F equals 11, it's reserved for something else. So that's where this F is like 2 bits of information, perhaps the 2 F's here. And you've got an instruction operand word, I don't know, here and here perhaps. And then the rest is used for literals. The 12-bit literal K. So how many letter K's do we have? 1, 2, 3, 4, so 8, 9, 10, 11, but then this is a least significant bit, subscript 0. So I guess there's 12 K's here. So all these K's will represent the 12-bit literal. I guess I'll just read stuff. Words 2. First word, second word. Decode, read, literal, process data, so I guess that's the cycle. And here's the example 1, LFSR 2, 0x123. The 2 signifies FSR 2, and you load it with what? Perhaps the RAM memory address 0x123? I don't know what it's showing here. Before the instruction, after the instruction. I don't know, but whatever happens after the instruction, 0x01, 0x23. Okay, so I'm just going to figure some out. 05, and in decimal that's just 5. But A5 in decimal is 165. I don't know. Stop and study it. I don't quite understand. Here's example 2, which is really just showing how to load FSR 0. and this is showing how to load FSR 1. I just don't know why on default it has these values in them, which is 5 or 165 in decimal. Okay, well that completes the LFSR instructions. So looking for more instances of FSR. It shows up in this move WF instruction and this INDF0 thing, which I've yet to understand. Okay, this is the glossary, I believe, section 37. Indirect addressing, I will read. When the data memory address is not contained in the instruction operates on the INDF address, which causes the data memory address to be the value in the FSR register. The execution of the instruction will always access the data at the address pointed to by the FSR register. And that's the last instance of FSR. So, maybe not expertly, maybe not perfectly, certainly not, but that does cover all the instances of FSR. Unless, of course, I should have chosen to search for file, select register, but I think I should have covered it all already. Yeah, there's when I type in file select register, there's 5 instances of it, but it probably would have found them all. FSR appears next to all of them. So thank you very much for watching this. I appreciate it. Hope it's helpful, and most likely you know more than I do, and you're like wanting to make a comment below to tell me stuff. So thanks for watching. Have a good day.